Hello everyone, I am Irene Mays Pilar. Welcome to the Waves and Optics class. This day, let's talk about the nature of light. We have a three kind of theory, which is the particle theory, the wave theory, and the wave-particle theory. First, let's talk about the particle theory. So what is particle theory? In Newton's particle theory of light, light is made up of little particles. They obey the same laws of physics as their masses like baseballs and planets. They are tiny, so the particles in two intersecting beams do not scatter of each other. The particles of theory of light is the explanation of the light propagation in the straight lines, except at the interfaces, was then easily understood. Still, the light particles were enacted upon by the invisible air. Newton did not publish his theory until 1704. After the death of Huygens, he was by then the best-known scientist in Europe. Isaac Newton in 1642-1727, he proposed the optic. Isaac Newton in 1704, Newton published his treatise Optics. This was 17 years after his great work Principia. He had waited until Robert Hooke died, since he had become so sensitive to criticism, especially from Hooke. Optics was written in English, not the Latin of Principia, and moreover, was much easier to read. It was very popular and revised it 3 times. Newton proposed the light consists of light masses. This means that a horizontal beam of light near to the Earth is undergoing projectile motion and forms a parabola. So the particle theory of refraction, it is a light particle deep within a medium, experiences no net force. Near an interface, example between air and water, light particles experience an attractive force towards the water. Newton imagined that water is made up of particles of some kind. Today we would call them molecules or atoms. When a light particle is deep within a medium, such as water or glass, it is surrounded on all sides by equal numbers of these particles. Suppose there is an attractive force between the light particles and the matter of particles. Then the deep within the medium, these forces cancel each other out there and there is no net force in the light particles. Then according to the Newton first law, the light particle will continue moving in a straight line since no net force acts on it. Near an interface, the situation is different. Now there are more matter particles on one side than the other, and the light particle can experience a net force. It would experience a brief attractive force towards the medium with a more matter particle. Around the 70s, Newton concluded that the light was a group of particles, or shall we say it is called corpuscular theory. Around the same time, there were other scholars who thought that light might instead be a wave or a wave theory. Light travels in a straight line, and therefore, it was only natural for Newton to think of it as extremely small particles that are emitted by the light source and reflected by an object. The corpuscular theory, however, cannot explain wave-like light phenomena such as diffraction and interference. On the other hand, the wave theory cannot clarify why atoms fly out of metal that is exposed to the light. The phenomenon is called the photoelectric effect, which was discovered at the end of 19th century. In this manner, the great physicists have continued to debate and demonstrate the true nature of light over the centuries. So, what is the corpuscular propagation by lens or the pinholes. At the same time, at the same way, one could understand the reflected light beams, mirrors, or the chattaran. The dependence of refraction on color was explained by assuming that force acting at interfaces depends on the color. The problem of simultaneous reflection and refraction is very hard to answer in a corpuscular theory. Newton's attempts were not satisfactory. Problems with the particle theory of light. In spite of the virtues of the particle theory of light, careful thinkers like Huygens realized that there were weaknesses that could not be dismissed. For example, at the interface, one never has refraction or reflection. Both happen with the relative intensities of the two components depending on the angle of incident. Number 2, if one makes a pinhole very small, the image of the light going through begins to widen instead of the narrowing, as you can see in the figure at the right. So the wave theory of light. Christian Huygens in 1629-1695, he succeeded in explaining almost all of the particles of light propagation known at the time, assuming that light was a wave traveling in a known medium. His theory, along with a detailed analysis of any cases, was published in 1690, very shortly after Newton's Principia, as the Traité de la Lumière, by assuming that the waves traveled at different speeds in different media, or reflection and refraction, were easily explained. The way in which waves propagate across the interfaces is easily seen by looking at the surface waves on the water. The speed depends on the water depth. Wave theory of light that compromise with wavelets, reflection, and refraction. So the famous Huygens constructions is shown at the right. We imagine at each point of the wavefront, another wavefront is emitted by all directions at equal velocity, unless it arrives in another medium where the velocity is different. In this way, by imagining the re-emission of the wavefronts after the successive short interval of time, one can build up the dynamics of the wavefronts. Reflection is easily understood as the radiation of the wave back into the medium. It is fairly obvious by symmetry that a wave incident at the same angle on the interface must have led to a wave moving out at the same angle to the interface. So this is the reflection in the wavelet theory from the Traité de la Lumière. The refraction is produced by imagining at the same wavelets now radiating into the new medium, but at a different velocity. One can actually show how all of this works purely geometric constructions, without elaborate mathematics. Note that simultaneous reflection and refraction is inevitable in this theory. This is the refraction in the wavelet theory from the Traité de la Lumière. Using the wave theory, Huygens could also explain more complex phenomena. For example, the ways For example, the way sound and light can be slowly refracted downwards because air density decreases with height, or the flickering light from the multiple light source like candle flame, where the sources themselves change in intensity with time. Huygens also understood that the way to understand wave dynamics in a crystal was to suppose that the crystal was made up of lattice of particles. He assumed that the medium, or the ether via which light was transmitted, was made up of tiny spherical particles through which compression waves could pass. In remarkable work, he treated the refraction of light through the Iceland spar or calcite, which splits a light beam into two beams. He was able to partly understand this. He was able to partly understand this in terms of wavelets, but not what caused it. Huygens also realized that the phenomena like diffraction, see at the left, had a natural explanation in terms of these waves. Although neither Newton nor Huygens realized it, they had uncovered key aspects of one of the most crucial questions in physics, the fundamental nature of light. It would need another 250 years to resolve it. As you can see, the figure fringes the diffraction of the Audubon de Hilbert Lyon obstacles. Wave particle theory. So this is a new theory. In 1905, the physicist Albert Einstein developed a new theory about the electromagnetic radiation. The theory is often called the wave particle theory. It explains how electromagnetic radiation can behave as both a wave and particle. In Einstein's argued that when an electron returns to a lower level and gives off electromagnetic energy, the energy is released as the discrete packet of energy. The theory possessed that waves of photons traveling through space or matter make up electromagnetic radiation. Evidence of the wave particle theory. So the evidence was discovered to support it. For example, scientists shone laser light through the two slits in a barrier made up of a material that blocked light. You can see the setup of this type of experiment in the figure below. Using a special camera that was very sensitive to light, they took photos of light that passed through the slits. The photos revealed the tiny pinpoints of the light passing through the double slits. This seemed to how that light consists of particles. However, if the camera was exposed to the light for a long time, the pinpoints accumulated in bands that resembled interfering waves. Therefore, the experiment showed that light seems to consist of particles that act like waves. So we have here the theory of particle and wave. We have the common concepts and contrasting concepts. First, the common concepts of the particle theory and the wave theory, that Newton's corpuscular theory stated that light consisted of particles that traveled in straight lines. Both particles and the wave theories adequately explain reflection from a smooth surface. When the two waves meet in step, they will add together to make larger wave by constructive interference. Light behaves as a particle and at the other times as wave. This complementary or a dual rule of the behavior of light can be employed to describe all of the known characteristics that have been observed experimentally, ranging from refraction, reflection, interference, and diffraction to the result with polarized light and the photoelectric effect. The electromagnetic radiation can behave as both wave and particle. Particles and waves should also behave differently when they encounter the edge of an object and from a shadow. Colliding waves that are out of step will cancel each other via destructive interference and produce a level surface of the water. For the contrasting concepts, Huygens argued that if light were made of particles, when light beams cross, the particles would collide and cancel each other. He proposed that light was a wave. Light does not always behave as a particle. Photon resembles particles outmoves like a wave. The particle theory also suggests that if the surface is very rough, the particle bounces away of the variety of angles, scattering the light also. The photoelectric effect seems to do the opposite. It favors the particle's model and cannot be explained by a wave model. The particle theory advocates envision that various colors were derived from a particle having either different masses or traveling at the different speeds. Light does not always behave as a wave. The shape of the arriving waves is strongly dependent upon how far the light sources is from the mirror. Light originating from a closed source still maintains a spherical, highly curved wavefront, while the light emitted from the distant source will spread more and impact the mirror with the wavefronts that are almost planar. Initially, we thought that the determination of the speed of light and the explanation of diffraction were critical experiments that eliminated the particle model in favor of the wave model. The interference effect is not restricted to light. Wave produce a surface of the cool or pound, will spread in all directions and undergo an identical behavior. That's all for today. I hope you've learned something. Thank you.